All right, so continuing our discussion of circuit elements, let's look a little bit more in more detail about batteries. So up till now, we have been treating batteries as though they were perfect, as perfect devices that have no resistance and pay their rent on time and do everything you want them to. And of course, that is not actually the case in real life. So what might keep a battery from maintaining a delta V that is the same as EMF? Well, batteries are made of materials and they're not necessarily perfect conductors. So batteries can have internal resistance, which makes sense from a logical point of view. And that's okay. We know how to handle that. So one way that you can think about it in your head, we can go back to that mechanical battery thought model. It, like I said, super, super useful model, even though it's not really how batteries work. So you can think about it like you've got this conductor pulling those electrons along with that non-Coulomb force and that Coulomb field. And basically you can think about it as though it has a squeaky belt. So you're not getting perfect efficiency as those electrons are coming over. And, we know that Fc and F non-Coulomb are in opposite directions. I'm going to draw an EC. So if force non-Coulomb is greater than force Coulomb, okay, so let's think about this in terms of a chemical battery. So with a chemical battery, you typically have an ionic solution within the battery. And so you have ions crashing around, progressing forward, but think about drift speed. Remember, drift speed looks kind of like this. It does go forward, but it takes a crazy path to get there. So that can impact the resistance of what's going on inside of the battery. So building on that, so drift speed is proportional to F net, and so drift speed would then be proportional to FNC minus E times EC. And so we can combine this with our conversation of conductivity and current density. So you get J is equal to I over A, which is equal to sigma E. And if we recall, the electric field is equal to F over Q. And so we have I over A is equal to J, which is equal to sigma FNC over E minus EC. And all we've done is just a little bit of algebra. And then what you can do is you can solve for the Coulomb field in terms of I, conductivity, and A. And you should do this on your own. And so you get the Coulomb field is equal to F non-Coulomb divided by E minus I over A divided by sigma. And so our battery has length S, with an E that is uniform enough. And so delta V battery is equal to the electric field Coulomb times the separation. And so then delta V is equal to FNC over E minus S over sigma A times I. So this is you have work divided by charge, which is EMF. And here you have units of resistance. And so this becomes delta V battery is equal to the EMF minus the internal resistance times I. So internal resistance is a factor of current. So the amount of current you're running through a battery will change its internal resistance. More current, more internal resistance. Or, sorry, rephrase. Internal resistance is this. More current will impact the delta V. The internal resistance is the same. So if our internal is small, and I is small, then delta V is equal to EMF. And this is essentially the assumption that we've been making, and sometimes it's good enough. Sometimes it's pretty close, and sometimes, well, we're just not going to measure more accurately, so it's good enough. But a large I can result in a measurable internal resistance. So essentially what you'd be doing is, in terms of how you would model the battery in a circuit, so here you've got your resistor in the circuit and the current's going around, and you'd model it as though you had a little resistor right after the battery. So it's pretty easy to handle in terms of doing these types of equations. But let's go ahead and, just like we have with all of our other circuits, we're going to use loop rule to analyze it. So you have EMF minus R internal times I minus RI is equal to 0, and we'll solve for I, and you get I is equal to EMF over R plus R internal. And so R internal is not constant for a battery. It is related to other external factors. So let's take a look at that. So for a 9-volt battery, R internal can vary from 1 ohm to 2 ohms. And yes, it can be that big. So let's say if we're going to look at this, we'll average this to be about 1.5 ohms. So we'll look at real current versus ideal current. So if you have a resistance of 50, I ideal is equal to EMF over R is equal to 9 volts over 50 ohms is equal to 0.18 amps. However, in real life, the current would be EMF over R plus R internal is equal to 9 volts over 50 plus 1.5, which gets you 0.17 amps. So a little bit of a difference. So again, it depends on how precisely you need your measurements. So this might be good enough, but it might not. Now let's look at if you had no resistance. So this would be a short circuit. So I ideal is equal to EMF over R, which is equal to infinity. No! Big problem. By the way, that's why short circuits are a problem. It's a circuit with no resistor or no resistance. If you've got some internal resistance on the battery, that's why it's actually a good thing. Then you would have 9 volts over 0 plus 1.5, which is equal to 6 amps. And by the way, this is why you never just connect a wire from two ends of a battery. You've got a short circuit when you do that, very little resistance. You'll run a ton of current and you will drain your battery. So let's not do that.